All right, so I put this plate file on the website, so just go ahead and download that, save it. Again, it's a step file, make it easy to bring into Workbench. Later on, I'll talk about the kind of integrating with SolidWorks. There's ways to connect that, so you can modify SolidWorks geometry, but here we'll just use a step file. And then, so I have Workbench open. So what I'm going to do is just drag in, go to my downloads, drag in that plate step file, and just drop it on my schematic. And I'll create a geometry block. We can import it by right-clicking on geometry, like we've done before, and browsing for it as well. But I think it's easier just to drag and drop it. So when you're doing topology optimization, it's going to be based off of a structural analysis. Okay, so you always got to do, that's your first thing, is you drag in a static structural. I'm going to drag in a static structural and drop it on my geometry. And so that's similar to what we've done before. The one difference now is we'll take the topology optimization, which is also under this analysis systems, and drag and drop that. Now you need to drag and drop that on your solution. That takes the solution from your static structural and does the optimization. So drag and drop your topology optimization onto solution. Okay. And now I'll give you these 3 blocks. Now, what I'm going to do is double click on setup, realizing your computer's going to take a while to catch up when that first time we open the mechanical. So just double click on setup, it's going to open the mechanical window. And once mine opens, I'll just kind of describe what we're going to do as your computers launch that. So the way, I just have this plate. Okay, so the way topology optimization works is you create kind of this blank canvas you can think of what your design envelope can be. And what it does, topology optimization, the key thing is it can only remove material, it can't add material. So you need to give it an envelope that's big enough where you can get a good design out of it. So here what I'm going to do is do a support. It's going to be fixed, basically a cantilever support. It's going to be fixed on the left, and it's going to have a load on the right. And what I want to do is minimize the mass of this. I want to have stress be below a certain threshold to minimize the mass. So I'll go through that exercise. But it's important when you usually define fairly simple geometries to start with, but it's important that it becomes kind of and it'll remove material from this to get to your design, as we'll see. So it's important to make that envelope big enough. And it's usually fairly simple like this. So what I want to do is, you notice I have 2 things here. I have a static structural on my tree and a topology. The static structural I'll set up just like I would a normal static structural analysis. So I'm going to do a fixed support on the left. Now you see the split line here. So this does have a top and bottom, even though it's symmetric. This little section here is where I'm going to apply the force. So that's the top of your beam. Okay, so the support's going to be in the opposite here. So I'm going to do a fixed support on the left, opposite of this section where I'm going to apply the load. And hit apply. All right, and then I'm going to apply the force to this little section. So I'll do loads, force, click that little area there that I created. I'm going to click apply. And then again, like we've done before, I'm going to do component forces based on the global coordinate system. So switch from vector to components. And then you can see that Y is my vertical direction. So I'm going to switch this to a negative. I'm going to do 500 newtons. Actually, mine's already in millimeters. Go ahead and change yours to millimeters now, because if you wait till after analysis, it'll give an error. So do units and in millimeters, kilograms second. That way our stresses will be megapascals, and we can specify our mesh size in millimeters. So go from units and switch it to millimeters. I'm going to do a force on that patch. I need to enter it. I forgot to enter the force. So negative 500 in the Y direction for that force. So negative 500 newtons is what we're going to apply. Okay. Now I didn't talk about material. This is structural steel by default. We'll just leave it as that. Yep. I fixed on the left edge here. So this is the fixed. If I click my fixed support, this edge right here. opposite of this patch where I applied the force. Okay. Now once I do that, I'm going to add 2 solution plots. I'm going to click solution, do a total deformation plot. Also going to do a stress, equivalent von Mises stress. So we'll be concerned about both displacement and stress. So I click solution, added the total deformation plot and the stress plot. And now I can hit solve. I'll just click on static structural. I'll just solve this first part. It's not going to do topology optimization yet. So I'm going to hit solve to get our initial results. Alright, and if I click on the total deformation plot, and I can click down on the graph and click the play button to animate it. So we just have a cantilever beam. I can also look at the stress. The deformation's 0.06 millimeters. The peak stress is 37 megapascals. So that's where my starting point is. But my goal is I want to get a design with reduced mass that still has a certain level of stiffness and a low enough stress. So once I run it, I can click on this, go down to this topology optimization section. It's going to use these results to remove the unneeded mass. So there's a few settings we got to make here. Actually, I think the defaults, we end up using the defaults here. So analysis settings, it just gives some control over the solver. Usually the defaults are going to be okay there, number of iterations and things. Optimization region, so what that means, if I click on optimization region, it gives me the design region that's this blue color. So that's the region that it's going to remove material from, okay? And then it has this the exclusion region, which it won't remove any material. It'll make sure it leaves material on these red surfaces. By default, it uses your boundary conditions because it assumes that's where it's going to interface with other parts. So you know, if you have holes or in this case supports, you want to leave material there just for the function of the part. It is possible if you had some additional holes in here you didn't want it to touch, you could add those as well to the exclusion regions. In this case, the boundary condition default behavior is what we want. But keep in mind you can have some control over where it can remove and not remove material. Objective. So let's go to response constraint first. So you set 2 things. You set a constraint of what you wanted the optimization to give you, and then you set some objectives. So response constraint, by default, we're going to reduce mass. And we're just going to leave this as default. It's going to reduce mass by 50%. So it has that goal in the optimization. And if I click on objective, we'll also leave this as default. What it's going to do is minimize compliance, or in other words, maximize stiffness. So we're going to leave that as the default too. So what it's going to do is reduce mass by 50%, the 50% of the mass that makes the stiffest part in the end, and subject to this loading that I've applied. Okay, so if I load it differently, I'm going to get a different result. So it uses the particular loading I've done here. So now I can click on topology optimization and just hit solve. It'll take a little bit. Let's pause this and. All right, so now it's finished the. Is it a question or? Okay, so it's finished the optimization, and actually, as it's solving, if you click this topology density tracker, as it's running, it'll update it as it's running. But now it's already finished. So once it's finished, you go to this topology density. Okay, and your solution, it shows you the shape it came up with. Okay. So the thing about topology optimization, it's kind of it gives each element, what it does is it weights each element from essential, a weighting of 1, to a weighting of 0, which means is not needed. And it's this continuum in between. So there's not an absolute boundary to your part. So what you have is this, when I click on topology density, I have this retain threshold slider, and I can move this left and right. Okay? And that'll give me, on the left, it'll give me more material. And if I drag it to the right, it'll give me less material. But at some points, I'll get designs that don't make any sense, right? So as I drag this to the right to 0.8, I'm getting something that's not even connected, right? So on this one, something around, maybe 0.5 or so, though it doesn't really make a lot of sense to have this extra little material there. Now on this one, I'm going to change one thing. I'm actually going to try to reduce the mass a little bit more. So if I go to my response constraint, and let's drop the mass to 25%. So again, I clicked on response constraint. I dropped the mass target to 25%. So I'll try to just retain 25% of the mass. Now if I click on this topology density tracker and just hit solve again, it's going to repeat the solve, but with that lower mass target. Now, when you're on that tracker, it'll show you what the geometry is at the current iteration. Yeah, I just hit solve. So I did change the constraint to 25%, and then just hit solve. Yep. So I can see the progress as it's doing that. Now, one thing, as the problem sizes get large, these topology optimizations tend to take a long time. So usually you want to start with a very simple geometry like we're doing here. So now it's done. Yours might take a little longer. So I have topology density. Now I can drag the slider. And now I get something that looks a little more logical, something that looks more like a truss structure that I would expect for kind of an optimal geometry of that. Another control you have, so you can play with that retained mass, and you can see that's going to change your result quite a bit. The other thing that affects your result quite a bit is your mesh density. So the finer, like I said, it's doing this element by element, right? Assigning a weight to each element, and it's doing some interpolation to find these boundaries. Basically using the shape functions like we saw in class. But if I make a finer mesh, they'll give it a higher resolution. So what I'm going to do is go to my mesh up on my model, and I'm going to change from sizing, I'm going to change that to from element size default. So again, I'm on mesh up on the top of my project tree, and I'm going element size and changing that from default to 5 and do it 5 millimeters. Okay, and once I make that change, I can just hit solve, and it's going to solve everything with that new mesh size. And I'll pause it again. Look at the tracker here. Alright, so you see, now if I go to the topology density, actually it depends on wherever I last left the slider. Right at 0.34 I have this. If I do 0.4 on this one, I actually get more like a truss structure. Now keep in mind, the only thing I changed between the last run and this run, basically this run added this little beam that wasn't there before, was the mesh size. So it's highly dependent on your mesh, the results you're going to get. So it's something, it's not, topology optimization is not really exact science. You kind of try different things and see how it impacts your results. Now, it used to be in ANSYS 17 that once you got this result, you actually had to just take a screenshot and bring that into SOLIDWORKS to even use the geometry. But now they've really improved that where you can work with this geometry directly. So what I'm going to do is go back to the ANSYS workbench window. Okay. Now it's important, actually, one last thing. So I go to this topology density. Wherever I leave this slider is what geometry is going to use. What I'm going to do now is run a verification run, use this geometry, apply the loads to it, and see what displacement and stresses I get. Okay. So as a verification of my design that I've obtained here, but I can't do it right now. I have to bring this into a new block. So it's important that your topology density, I have mine set to 0.4. It doesn't have to be exactly 0.4, but just choose wherever you want, what geometry you want to test. And so it's important you have that value entered because it'll use that geometry. Now, I go back to my schematic, and it has, what I do is right-click on results on my topology optimization. So right-click on that. And then what I want to do is transfer to design validation system. So what that's going to do is create another static structural with the same boundary conditions, and it's going to feed this geometry into it so I can actually validate it. It'll take a little bit for that to happen. And so there's a couple things we have to do here. Actually, I'm just going to rename the second static structural to verification, because we're verifying that the solution we got are the topology optimization. On the geometry, you have to so there's a couple steps we got to do. We got to right-click geometry. I don't know why it always forces you to do this, but you have to do the update thing. So right-click the geometry on that new static structural created and do update. And that takes way longer than it seems like it should take, especially on those computers. So we just got to wait for it to do that. And what I'm going to do is once that is updated, I'm going to after it's updated, I'm going to double-click geometry, and that's going to bring up what's called a space claim. It's basically ANSYS version of CAD software. And what space claim does, it makes it really easy to work with this mesh geometry that you get out of, as we'll see, that you get out of this topology optimization. So I'm just going to, once that finishes, the update, once that red light goes out on the lower left of your screen, it changes the icon for geometry. Once it does that, you can double-click geometry, and that's going to open space claim. And actually, I'm going to just pause it for a moment. All right, so now basically what it's done is it saved that geometry as an STL file. So basically as a solid file, a mesh file, and it's loaded in the space claim. So like I said, it's ANSYS CAD software. I realize a lot of you aren't able to get to this point because of the computers being, slow. So, but I'm recording this, so when you're working on it later for your projects or whatnot, you can refer to this. So what it's giving me is my original geometry, and the reason I can't just click on, if I go into model now, I'll just get my original geometry, which is not going to help me. I need to convert this space claim this mesh into a solid, okay? So it has on the left, and the space claim allows me to quickly do that and allows me to clean up the geometry pretty easily so I can get something that looks reasonable. So the first thing I'm going to do is right-click this first item. This first item is just the original geometry, okay, that plate. I'm going to right-click that, and I'm going to say suppress for physics. And what that does is that when I load this into Workbench, it's not going to have that in there. And I can click this check next to that, and that plate will go away. And now I'm just left with the mesh. So I unclicked this top item, and I right-clicked and said suppress for physics. And that leaves me with just the mesh. Now what I want to do is convert this into a solid. Now, I don't want you to do this, but one way you can do it, if you just want to do a quick run, and you don't want to deal with cleaning it up, you can just right-click and say, actually I have to expand this. There's my facets, or the mesh, basically. I could right-click it and say, don't do this, but you could say convert to solid. Okay, and that would just make a solid out of there. But I want to clean this up a little bit, especially because it has sharp corners, and that's really going to cause stress concentration, so it's not going to give me accurate stress for this design. So what I'm going to do is convert this into a solid and clean it up a little bit. So what I'm going to do is we're on the design tab by default. Takes a little bit to get used to. So space claim, the mouse controls are the same. So middle mouse rotates, control middle mouse pans, and the wheel. So fortunately that's the same as ANSYS and SOLIDWORKS. So you work with the screen that way. And then what we want to do is start a sketch. We're going to sketch, 2D sketch, and extrude it. So to do a sketch, on this main design tab you have mode. We're going to switch to sketch mode. Now by default it picks a plane that's on the bottom of the part. That's like the default top plane. But if you move your mouse over the screen, in my case towards the bottom, it will create a plane that is normal to the view, which is what I want. So just find a plane that's normal and click that, and I'll create your sketch plane. Now if you accidentally have a different sketch plane, let me exit, go back to 3D mode here. If I go to sketch mode and I end up on this bottom plane, you can change your plane by clicking this pencil icon on the bottom, select new sketch plane, and then I can get back to that ability to select my plane that I'm on. So again, I'm just moving the mouse around until it picks that bottom plane up. Okay. Now once I have that, it gives me a silhouette, basically the intersection of that geometry onto that plane. Okay. And what I want to do is select all those edges. So I'm just going to draw a box around them. Click drag, draw a selection box around all that geometry, those edges from that mesh. And then what I'm going to do is on the design tab there's a copy button and a paste button. So I'm going to do, so first thing I do is select, after I get my plane, select all the geometry, just with the box select. Then I'm going to click copy or Control C, and I'm going to do paste or Control V. So copy then paste, and what that does is it just puts that geometry on that sketch plane. Okay. So again, if I could, you can use Control Z to undo things. So again, I just selected all the facets from my sketch plane, copy, and then paste. Now once I do that, on the left I want to uncheck my facets because I don't need those anymore. Now I'm just working with my sketch. So I just have this curves thing that it created when I pasted that. And now the reason I do that is because I can now edit these. I couldn't edit the original facets, but now I can edit these curves to kind of clean up my geometry. So you can see the edges are kind of jagged here just because of the coarseness of the mesh. It's not an exact thing, so we want to clean this up. And this is kind of what space cleaning is good at. So what I'm going to do is select all, once I pasted them, I'm going to select all the edges again, and they may have been selected just by default, so I'm going to select all my edges. And then I'm going to go to the Repair tab, okay? And one of the options there is to fit curves. And what that does is it fits lines and arcs to the sketch to make it more smooth. So I'm going to fit curves. And I get some options on the lower left here. So, and if I zoom in a little bit, you can see what it's doing. I have the green, which is my original, and then this kind of reddish black lines here that are the new lines it's creating. And it has this maximum distance, so that's how much air it'll let it have at any point. The more air you let it have, the smoother the geometry is going to be, the further from the original geometry. So for example, if I change from 0.53 to 1 millimeter and just hit enter in that box, it'll be a little more smoother, but it has up to 1 millimeter of error, right, or difference between the original geometry. So I think on this one, 1 millimeter works pretty well. And the other thing you can do, it defaults to lines and arcs. You can't have it do splines. If I click that, it'll get a closer approximation, but it's also a little more complicated geometry. So I'll just leave it as arcs and lines. So you could do splines if you want. There's nothing, there's no issue with that. And you can click this correct tangency. Sometimes it works, and sometimes it makes it have disconnected regions. So you can just try that out. In this case, it's working to have the correct tangency. And what that does is when edges are close to tangent, it forces them to be tangent. It's just as part of the simplification. So once I get that the way I want it, and again, you just kind of play with this maximum distance number to adjust that, then I can click OK, this checkbox on the left of my screen. So I click OK. And that gives me the updated geometry that's now smoother as compared to that original geometry based on the mesh. Okay. Now I want to round off some of these corners because those are going to cause stress concentrations. So the way to do that, I'm going to go back to my design tab, and one of the options there is pull. So in Space Claim, pull allows us we can work on it in 2D. Or pull also allows us to extrude in 3D, so it's kind of a general tool. So I'm going to do pull. Now what it's going to do is it changes that to a surface. So it knows we want to work with this surface. But in order to make this work correctly, we need to delete these interior areas. So it's made everything green as a surface. So I'm just going to click each of these interiors and just hit delete. Okay, because I don't want to have material in there. So I just click it, each of those interior areas, and hit delete. And then what the pull tool allows me to do, I'm still in the pull tool. If I click a vertex, like I'm going to round off these corners is what I'm going to do. So if I click a vertex, and I just have to hover the mouse till I get a vertex, and then I can pull on this arrow, and it's going to add a radius. Okay, so just a quick way to add a radius. And here I'm not so concerned about what the exact radius is. I'm just trying to round these off so I don't have a stress concentration. So again, you just click each vertex. And if it's trying to make you do it in 3D, it's because you haven't deleted these interior areas. And then I'll click this and drag that. So I'm just cleaning up these sharp corners. on the model. And depending on what you started with, you may have a different number of corners. Alright, so that's pretty much the way I want it. So now I'm ready to kind of extrude this. So the last thing I do is I'm still going to stay in the pull tool, but if I click the area instead of a vertex, just click the area and click and drag it, and it's just going to extrude that area normal to the surface. Now it made it way too big, but it gives me this dimension that shows up, and I'm just going to enter 5. The thickness is 5 millimeters, so I'm going to enter 5. Now if you happen to not enter the right depth, you can Control Z and just go back and do the pull tool again. Control Z to undo, and then do the pull tool. Oops, I missed the option to enter. The one thing about Space Claim, it only gives you one chance to enter the dimension. It's not letting me. Let me try that again. So I'll enter the 5 and hit enter. Try that again. I wonder why it's not keeping that box up.
If you hit 5 while you're holding it with your mouse.
Yeah. It seems like if I click the surface and then drag it, it leaves it up. Otherwise, but yeah, if you hit 5 while you're dragging it too. So I hit enter. I don't know why it gives me that error, but it seems to be working now. Now the last thing I need to do is I need to put that split line in. Now oftentimes, this is another thing Space Claim is good for, is you need to add split lines so you can apply boundary conditions in certain areas. So if you haven't did it in SolidWorks and you're just working with like a step file or something, Space Claim provides a quick way to do that. So on the design, on the intersect, I have a split. And if I just click on this top surface, I need to put that split for where we apply the force. So if I just click that top surface, it gives me a little point on that surface. And it gives me 2 dimensions or 1 dimension. What I want to be is on the edge. I just want to split it in one direction. So I put the mouse on the edge. And it gives me 2 boxes. The top one's the percent along the edge that I am. The second box is the distance along the edge. I want to enter the distance as 10 millimeters. So if I hit tab, so what I do is, again, I'm in the split tool. I click the top surface and then drag the mouse around, or just move the mouse until it's on the edge. Then I'm going to hit tab to get to the second box. I can just get as close to 10 as I can. It doesn't really matter if I'm exactly 10. So I'll just get close to 10 millimeters and click, and it makes a split line there. So I'll be able to apply that. And this is really useful if you're on your projects, you're bringing in the model, you need to add split lines really quick. It provides you a quick way to do that. All right, so once I'm done, I got it to a point where I can do the modeling. So I'm going to do File, Save, File Save, and then File Exit Space Claim. Okay. The other thing you can do from Space Claim is export these models as a step file. If you wanted to bring it into SolidWorks and use that as a basis for making your model, you can do that as well. So now I'm going to go back to my schematic, and so I've updated my geometry. So I'm in my verification block. So I'm going to go into Model, and when it says, would you like to update upstream data, say yes. And that'll allow me to apply the loads to this optimized geometry. Okay. Alright, so now I have the geometry that I created in Space Claim. Now if you don't do that Space Claim step, it'll just, like I said, it'll just bring the original plate back in. So you do need to at least create a solid in Space Claim to do the verification. So now what it does is it has the same setup, but it doesn't know what surfaces correspond to which surfaces. So you do need to reassign your surfaces. So fix support, I need to re-click this left edge, and the force, or we need to re-click that top surface, just to let it know where those surfaces are on this new geometry. Then I'm just going to hit solve, and it'll run the analysis on this structure. And we can see what the stress and displacement are. Now, one thing you'll see, sometimes when people are working on a project, they'll see this warning, at least one body has been found to have only one element and at least two directions. So when that happens, if I look at my mesh, it's not liking this beam area here where I only have one element vertically and one element horizontally. So that's what it's talking about. And to address that area, you just kind of reduce your mesh size, at least in those regions where you see that it only has one element thick in both directions. In this case, it doesn't affect the results too much, so I'll just ignore that error. But that's when you see that error, that's what's going on. Because sometimes people see that as they're working on their projects. So total deformation and equivalent stress. So I got a peak stress of 125. Now, one thing on this model, if I was concerned about that peak stress, let's say my peak stress could be 100 before failure instead of 125. So it does allow you, I want to show you one more thing. If I go back to the original setup here, I put my response, my constraint as mass before. But sometimes it doesn't allow you, you don't know what the stress is going to be though. So sometimes you want to control what the max stress is. So you can change it from mass. So this is my topology optimization. I'm changing my response constraint where I had 25% mass retained to a global von Mises stress. And I'm going to say the max stress is 100. Okay. What that's going to do is find the structure that gives me a mass, a max stress of 100. Now I do have to change one other thing though to make this work. If I ran it right now, it would just give me the whole block because what I have under my objective is to maximize stiffness. Well, if my objective is to have stress below 100, maximize stiffness, it's just going to use the whole thing. So I need to tell it that my response is to minimize mass. So now it's going to keep stress above 100 but minimize mass. And that will give me a slightly different geometry. So I just want to point out that you can control, instead of targeting mass, you can target a max stress. And in this problem, I don't have time to go through it now, it'll give you a slightly different geometry that will actually be under 100 megapascals. Actually, if I open, I should be able to open one I had to before. Let me show you what it looks like when you go through the exercise of reducing the stress to under 100. Okay. So if those exact settings I just had it on, if you go through that process of redoing the geometry, you'll end up with this geometry, which after you do the stress, it was 125 before, and I set the maximum to be 100, so now a maximum is under 100. So you can target stress while reducing mass. Here I'm getting a slightly different geometry where it's more, you can see that all the geometry is a little smoother in this one. It's kind of a more organic shape. Because before I was maximizing stiffness while reducing mass, which it doesn't really matter about sharp corners and things. Here I was trying to have a stress below a certain level, which forces it to have more smoother geometry to have less stress concentration. So you can get different results depending on how you set it up, which kind of makes sense.